Audio Jungle. Audio Jungle.
All right. So we have axial flow turbine, right? Today's topic. Axial flow turbine. AFT. All right. So basically, what is the work of turbine? You know that. So turbine basically used to in turbo machinery or in uh, jet engine if you talk basically. So turbine work is what basically to produce work, and how it will produce work. It's like a expansion in turbine. Whatever the products you had seen, basically, see this is what compressor. This is what turbine, right? So generally what will happen here, this is what air intake, okay, this part is what diffuser, you know that, this is what compressor, you know this, and this is what combustion chamber CC, and this part is what turbine, and this part is nozzle. All component now you are aware, okay. Now this turbine basically whatever the combustion products, this is the combustion chamber, this combustion chamber products are very high pressure and very high temperature, okay. In combustion chamber whatever the products you have, combustion products, because you have increased pressure here. In the diffuser you will do the same thing, like in diffuser what you will do, basically in diffuser you will raise the pressure, and pressure will rise, then obviously temperature will rise. Similarly in the this compressor part, here also pressure you will rise, static pressure I am saying, then temperature also will rise, okay. In the combustion chamber what you are doing, you are burning fuel, m dot f. If you are burning fuel, combustion is what happening here. So what will happen again, in combustion chamber itself pressure will rise and temperature will rise. So ultimate what you got, very high pressure and very high temperature in combustion chamber. Now so this high pressure and high temperature gases, combustion products, will try to expand, okay. So that expansion, so up to here this in diffuser to, you can say diffuser to compressor, what was there, it was compression, it was compression, means conversion of kinetic energy into pressure energy. This all you know, I know, because everything I have explained in jet engine, turbo jet, in jet propulsion basically, but just I am trying to relate this component turbine, okay. So compression occurs in diffuser as well as compressor, but coming to the this turbine and this nozzle, both places will have expansion. Will have expansion. In expansion what will happen, very high pressure and high temperature, basically high pressure energy will be converting into kinetic energy, okay. So here what will happen? This kinetic energy will be converting into pressure energy, hence velocity here decreasing, but pressure and temperature is what rising. But at the same time here, when pressure energy will be converting into kinetic energy, so whatever the pressure and temperature will be decreasing. Why? Because this high pressure and temperature will be converting into kinetic energy. Expansion takes place. Okay, so in turbine what will happen? Expansion takes place. So here now velocity will be increasing. Ultimately here at the exit you will get very high velocity. High exit velocity you will get. So this is true, like the most of expansion or the highest kinetic energy you will get in nozzle, because at the part, that last part which is the nozzle, so that nozzle work itself is what, to accelerate the flow as much as possible so that you can get highest exit velocity and your aircraft can propel in forward direction properly. That is the main thing. Okay, but this expansion will be starting from the turbine itself. Okay, so that expansion basically will do things. One, velocity will be increasing, that is true. Another, this high pressure and high temperature combustion products will do work over the turbine blades. Once it will do work over the turbine blades, then turbine blades will start rotating. And once turbine blade will start rotating, then you will say turbine is what, producing work. Okay, and obviously this work will be supplied to the compressor and this will be continuous process. All right, so this expansion will do basically two works. One, it will start doing work over the turbine blades, so work will be produced by the turbine. All right, and second thing, obviously kinetic energy will be increasing, velocity will be increasing, and then further kinetic energy will be increased in nozzle, and finally you will get highest exit velocity. So whole the process now you understood, right? So now in the turbine, how that work will be produced? Okay, how that work will be produced or how that work will be generated by the high pressure and high temperature energy of the combustion products. How this combustion products will be used to produce work in turbine, that now you are going to study. All right, so now only one component you will have. So generally this is what turbine. Okay, and this turbine is what you will get like this. And very high pressure and high temperature, very high pressure and high temperature, okay, energy combustion products will try to rotate the turbine blades and hence it will be producing work, WT. It will be producing work. So this turbine is what, basically work producing component. It's a rotatory component as well as work producing component. At the same time, compressor you had seen, it was also a rotatory component in jet engine, but it was work absorbing device, okay, or work absorbing component. And nozzle and diffuser, you know, it's both are stationary component. They're only transfer of energy. Anyway, so how this work will be produced? So same thing, just like in compressor we had stator and rotor blade, here also we'll have rotor and stator blade. Okay, so now we'll start from the component first, and then through the component we'll go directly to the velocity triangle. Okay, because the more theory if we go, then obviously theories are available, but I will suggest it is not required. We should directly hit to the velocity triangle and we can formulate the required formula, and then we'll go for the numerical as per our gate syllabus. All right, anyway, so here for this turbine also we'll go for the analysis, and that analysis is what, inside the turbine. So inside the turbine what we have, we'll draw the diagram. Here also we have a component which is nothing but basically stator and rotor. So the stator as a static part, and that also called sometimes nozzle. Okay, stator and rotor. Rotor is basically rotatory part, and stator is basically static part, just like in compressor. But here sometimes stator will be called as a nozzle. Okay, and both this nozzle and rotor, or you can say stator and nozzle, rotor, will make one stage, and stage definitely will produce, this stage will be basically producing the work, and what is the degree of reaction for the stage, will find it, and what are the stage performance parameter, that also will find. That is our job, and these are the 2-3 points what I have told you. These are the syllabus of your GATE aerospace, all right, and we are following the pattern of GATE aerospace, that's all. Otherwise, if you go this turbine turbo machine itself a big subject, so we don't have to involve in that so much topics. Whatever our syllabus, we follow that, all right. Now, so here the turbine component, basically components. So these are obviously rotatory part, which is rotor. Stationary part, this is what? Stator. This stator sometimes called as nozzle. Why it is said nozzle? Because you know the work of nozzle, it will used to accelerate the flow, so it will be converting pressure energy into kinetic energy. And I in starting only I told you this turbine itself is what converting pressure energy into kinetic energy. So this, just like if you see the difference in turbine and compressors, in compressor this was rotor and this was uh, basically diffuser, or called as a stator. So stator was diffuser. Diffuser was used to diffuse the flow, means kinetic energy was decreasing and pressure energy was rising. That was the thing. So you just check. And rotor is what in both it is common. Okay. Here this rotor, here fluid will be working. Fluid works on rotor. Okay, but in compressor, what was in compressor? If you remember, in compressor I told you, in compressor that rotor blades was doing work on fluids, hence that relative velocity was decreased, if you remember. I told you why that compressor, in compressor, why that relative velocity after the rotor, why it is decreased. So basically decreased in the sense it was taking work from turbine and supplying to the fluid. Yes, so that was the thing, and because of that absolute velocity was increased after the rotor and relative velocity was decreased, if you remember that, right? So here it is just opposite. Here the fluids, whatever combustion products is what fluids, and combustion products is what doing work on rotor blade. Okay, hence it is the work producing, and their rotor was were doing the rotor's blade were doing the work on the fluids, coming fluids, hence that work was the absorbing work, and compressor work is what negative, and here turbine work is what positive. All right, anyway, now so we'll have a rotor and stator, so I will show that diagram. So it is see, suppose this is the very generic diagram I am drawing here. You say this is what rotor part. Okay. This rough diagram I'm drawing here so you can get the idea. All right. Anyway, and hot gas, because these gases are coming from the combustion chamber. So this is what hot gas is. Okay. This part is basically, I'll give the naming. This is what I told you, it is called nozzle or it is called stator. This is the rotor. Okay. This is the basically disc. Okay. And here we have exhaust. If you go for the numbering, so the same thing here also, this is like hot gas here. Okay. And this is the same thing, is stator or nozzle. This is what rotor. So numbering I'm just going to give. So numbering will be 1, this is what 2, and this is what 3. All right. This is the diagram. All right, so I can draw separately here. You can see here, this part is basically two and 3, and this is what you can say 1. Okay, so this 2 to 3 is the rotor. This is what 1 to 2, you can say this is what is stator or nozzle, it's your choice what you want to say. I told you nozzle or stator. All right, so why stator or nozzle required first? Because in combustion chamber, I told you when I taught that jet propulsion, so in combustion chamber we are using turbulence. Why turbulent? We are using that device because we want to create turbulence flow so that there should be a proper mixing of the fluid, that air particles as well as fuel particles. So one device which will produce circulatory motion, it is basically used to create turbulence in the combustion chamber so that there should be a proper mixing. So at the same time we are using even fuel injector. Okay, and igniter in that, so turbulence will be there, and that flow will not be smooth. It will be kind of circulatory motion as like it is required actually, proper mixing. So directly we cannot allow this circulatory flow to the rotor blades. Why? Because rotor is the rotatory blade, okay, and if it is rotating and at the same time when circulatory flows are coming and going to hit, so it may hit with different angles, so there may be chances of the breaking of the rotor blades also. That is also one more reason. Whatever the flows are coming, we are directly allowing it to the nozzles, and this nozzle will definitely, it is stator and it will be just like an inlet guide vein, so it will direct the flow also, and then it will enter to the rotor. So this is the thing. Now we'll talk about the velocity triangle, okay. So for the, just like a compressor we had seen, so we'll talk about the velocity triangle. So in velocity triangle, what are the velocities component, that we also have to see. Anyway, this is the one thing. Second thing, the same diagram for we can draw the with respect to the radius also. So this diagram will be like this, see, the same. This is what turbine, we just say this is what turbine. So we are taking this section here, okay, and this is the base, you can say. Okay, now the blades are here connected with the rotatory shaft. All right, and this is what rotor, and this is what stator, which is okay. Now passes for the flow. This is what nozzle, it is stator, and this is what rotor. So this part, it is called tip, and this is called root. Why I am drawing this? Because hub or root or hub meaning is same, okay. I will write here hub, because sometimes they will give the radius, hub radius and tip radius, so that time it should be very clear. So this radius from the base, okay, this is called R tip. tip radius, and this radius is called from here R hub. Okay, this diagram you need to remember. Anyway, okay, now so we'll go for the here we have a flow. We'll go for the velocity triangle for this. Velocity triangle. Okay, now as usual, like same velocity pattern will follow just for the we had followed for the uh, what it is called compressor. So same thing we'll do for this also, so there should not be any kind of confusion. Okay, all right, now so for the velocity triangle we are having here the velocities, different type of velocity. So first is called blade or peripheral velocity. Okay, or peripheral velocity, it's called peripheral velocity or rotational speed or blade speed. So it is what u, because it's an axial device, so u1 is equal to u2 is equal to u, which is constant, because we are talking radial sorry axial turbine. Okay, so for axial this one is constant because diameter is what constant. Then this is number one. Then we'll go for number two. This is nothing but absolute velocity component. Absolute velocity. Absolute velocity, and it will be denoted by C. Okay, C1 comma C2 comma C3, absolute velocity. Third will go for the relative. Okay, or we'll write axial velocity here first. It is CA1, CA2, CA3. Okay, and at the same time the viral component, which is nothing but CT1, CT2 and CT3. Okay, then we'll go for the, because we have a rotor, so relative velocity will come, so it will be omega 1, omega 2, like that. Okay, these are the velocities, and now we'll have a angle also. Okay, what are the angle? The angle are air angle, All right, see this for the velocity triangle, these velocities are required. Okay, just like compressor, same thing we are going to do, and I have told you that velocity is vector and all. Okay. Anyway, so now we'll go for the angles. So these angles are air angle. Okay, and these angles are air angle, and these are alpha 1, alpha 2, or alpha 3, whatever it is required, we'll do that. Next is the blade angle, just like in compressor we had seen. Blade angle, it is beta 1, beta 2. All right, these are the angles. Remember, this alpha is the angle. Okay, alpha is the angle between absolute velocity. Let me write complete. Between absolute velocity with axial direction. With axial direction, and this beta 1 and beta 2, these are the angle with the between relative velocity. With the axial direction. Okay, so there should not be any problem now. So I will draw the velocity triangle finally. So see, this is the, because in compressor I had explained nicely this triangles, because inlet and exit we are going to draw for the rotor. So here I'm trying to go in short, because in uh, compressor we had done nicely. So okay, just say this is what axial, and from the axial direction this is what inflow absolute velocity, and this is nothing but alpha 1. Okay, alpha 1. And now these are the stator blades. Flow will be entering here. Okay, this is what is stator or nozzle. No, I told you both are the same thing. So this is what is stator. Now flow will be going. Now this flow will have a relative component as well as absolute component. So because rotor will like uh, get only relative velocity, it will, rotor will recognize only relative velocity. So for that reason you have to be aware with the relative velocity, because for the rotor relative velocity is important, nothing any other velocity, relative velocity, because that in compressor also I told you why. Okay, so similarly here you can draw. So now this is the velocity component. Okay, this is what relative velocity, here it is W1, this is the blade speed u and this is the absolute velocity c2. Okay, now next we have a rotor. So this rotor will be here, and here in this rotor as I told you, it will recognize only, and this rotor is what rotating. Okay, it will recognize only relative velocity, hence. So inlet for the rotor will be relative velocity and exit will also be a relative velocity. So this is the now exit. For the rotor, this is what exit. Okay. And this exit velocity will be, okay, you can say this is what better, because this is the point 2 we are taking. So there should not be any confusion. This is C2, so hence this is what W2, because this is the point 2 we are talking. Okay, so this is W2. Now this will be what? Exit will be W3, because rotor is what between 2 to 3. So W2 and W3 for us it is important, and definitely this will be what? U. Okay, and this will be C3. All right, from axial this angle will be beta 3, and for C2 this angle will be alpha 3. Similarly here, from the axial this angle will be for the relative, here I have written beta 2 is the angle between relative velocity with the axial. Here see, relative velocity and axial. So see, this is W2 is relative velocity and this is the axial direction. So this is what? Beta 2, and from axial to absolute velocity this angle, it will be full angle, it will be the alpha. Okay, so this is the separate diagram here I have drawn. I hope this one is clear to you. And this one is basically 1 to 2. 1 to 2 is the stator or nozzle, and 2 to 3 this is what? Rotor. So this part is what? Rotor, no? So for the rotor, this is the inlet triangle for rotor. This is the inlet triangle and this is the exit. So for us this inlet and exit is important. Yes or no? Just for we had seen for the compressor. Okay. Anyway, so this is the one way to draw the triangle. I mean separate component you have taken for stator. So for stator obviously absolute velocity will be there and it will enter with the absolute velocity. So C1 is the absolute velocity for the stator. Okay, and after the stator what will have? A rotor. So for the rotor we should have inlet triangle and exit triangle. So before the rotor, if you check, inlet velocity triangle is given, and for the rotor definitely relative velocity will be entering to the rotor, hence W2 we have, and W2 velocity component with the axial angle is what? Beta 2. Okay, everywhere if you want you can draw, this is what? Axial velocity, no? CA. If you want you can draw here, this is what? CA. So this will be CA. Okay, and this will be CA. Similarly here also this is the CA. It's your choice if you want to draw. This is what? CA. Okay, so and absolute velocity we will have, which is nothing but C2. That is the inlet triangle, and exit triangle, if you check, obviously flow will be exiting from the rotor blades with the relative velocity. So W3 will be the relative velocity, again beta 3 is the angle, and absolute velocity will be there. So alpha 3 will be the angle from the axial. So this is what velocity triangle. Now another also, in different way also, if you follow a veganization, so I will give one more triangle. It's your choice what you want to follow, but meaning will be same for both. Okay, so this is the one velocity triangle, just for understanding component wise. This is the another complete velocity triangle you can see here. So this one is given in veganization, so I'm just going to draw the same. Check, we are having first stator, right? And so for stator we will draw check this. Here flow is what going to enter. So flow will going to enter, so it will enter with the absolute velocity. Yes or no? It will enter with the absolute velocity. And what is the absolute velocity here? It is C1. So this velocity is nothing but absolute velocity, and it is C1. And what is this angle from the axial? Obviously it will be alpha 1. Okay. Now here we have a stator, or called nozzle. So these are nozzle. Okay, all right. Nozzle blades, or you can say stator, it's your choice. Nozzle or stator. Now after this stator, because this part I just want to draw in large way so you can understand easily, should be very clear. Now, so after this, if you check the stator, so what will be the outcome? It will be relative velocity. Relative velocity for what? For the rotor. Okay, so this component will be, this is 1 here, this is 1, I can say this is the 1, this is the 1 part, this is 2. So entering will be relative velocity for the rotor. So for this rotor, obviously relative velocity we will have, and then we'll get rotor here. Okay, this is what rotor. Right, this is what rotor. So with this rotor, anyway, so with this rotor flow will be exiting, and with what velocity it will be exiting? It will be exiting with the relative velocity again. And with what velocity it is? Omega 3. I hope this one is now clear. No? Separate I am drawing. So once it will be completed, it will be clear to you. All right. So this is W2, relative velocity inlet, relative velocity for the rotor, and this will be obviously axial velocity, and here we have stations 2, so this will be CA2. Okay, and this velocity will be absolute velocity, and it will be C2. From the axial, this angle will be beta 2. From the axial, this angle will be alpha 2. This should be very clear. Okay, already I had explained. All right. Now this is nothing but U. Okay, this will be WT2, and the whole length will be, it will be spiral component, which is nothing but CTT2. That is the component of absolute velocity. WT2 is the component of relative velocity. That already I had discussed in compressor, so I am not going into that. Okay. This is what rotor blades. This is what rotor blades. Okay. All right. And the exit is what? W3. Now for this also we'll draw the triangle. So this is the relative velocity, and somewhere here we have obviously axial component, so this will be axial component, but it will be CA3. Somewhere we have absolute velocity as well, so this will be C3. From the axial, this velocity, this angle will be B3, beta 3, and this angle will be alpha 3. Similarly here, the component of absolute velocity will be swirl component, which is CT3, and the vector sum of the relative velocity as well as absolute velocity will be the blade speed, which is U, and the component of relative velocity will be WT3. This is the whole triangle. Okay, if you check now, obviously because it's an axial, turbine, so U1 is equal to U2 is equal to U is constant. At the same time, CA1 is equal to CA2 is equal to CA3 is equal to CA, which is constant. Okay. Now if you go for the numbering, this is 1, this is 2 for this. So obviously this till this point it will be 2. Then this is the third point. Okay. This is the third point. So what is in 2 to 3? 2 to 3 is the rotor blade, and 1 to 2 is the nozzle. Here already I had given 2, 3, this is what rotor, and 1 to 2, this is what nozzle or stator. So if you check from this, where is the inlet triangle? So this is what inlet triangle, and this is what exit triangle. Exit triangle. Okay, inlet triangle and exit triangle. So from inlet triangle, what we have? From inlet triangle, what we have? Check mathematical calculation. So you will get that CT2. Check complete CT2 is what? U plus WT2, number one. Then from the exit triangle, what we have? From exit triangle, if you check, it's a basically WT3 is equal to U plus CT3, right? So this is equation 2. Now from equation 1 and 2, if you check from equation 1 and 2, I will go little fast now because it's a trigonometric relation only. From equation 1 and 2, what we have? U is equal to C. U is equal to CT2 minus WT2. And from the second equation, what is the U? U is nothing but WT3 minus CT3. WT3 minus CT3. Or what you can say, it is CT2 plus CT2 plus CT3 is equal to WT2 plus WT3, right? This is the one very important relation for the axial flow turbine. This relation they can ask, okay? Make a point. Now from the same if you check from triangle, from input and exit, both we need to check. What is the tan alpha 2? Check from the triangle. Now you have triangle. What is the tan alpha 2? It is CT2 by it is CT2 minus WT2 by CA or CA2. Yes or no? Check that triangle. Tan alpha 2 and tan alpha 3 we need to find. Tan alpha 2. Sorry. What is the tan alpha 2? Where is the alpha? It's a complete angle, right? Alpha 2 is complete angle. So you can get CT2. And alpha 2 is the complete angle. So CT2 by CA2. CA2 is CA. Huh? So similarly we can get tan alpha 3 full. Alpha 3 is the full angle. Yes, here also. No, alpha 3 is this is small angle. So this angle only. What is the tan alpha 3? It is CT3 by CA. This one is the axial velocity, CA3. CA3 means CA. So I can say here, you can check triangle and you can get tan alpha 2 will be it is nothing but CT2 by CA. Similarly tan alpha 3, check the triangle, CT3 by CA. Similarly from the triangle we can have tan beta 2. Check the triangle. Tan beta 2 is WT2 by CA2. No? CA2 is CA. So WT2 by CA, tan beta 2. Similarly tan beta 3. Beta 3 is the complete angle. So it is WT3 by CA3. Right? So I can write here tan beta 2 is nothing but WT2 by CA. Similarly I can write tan beta 3 is equal to, check the triangle, WT3 by CA. All right. Now everything you have now in terms of trigonometric relation, you can keep this. So CT2 plus CT3 is equal to WT2 plus WT3. What you will get? You will get tan alpha 2 plus tan alpha 3 is equal to tan beta 2 plus tan beta 3. Right? Yes. So this is the relation. This is also very important. This is also very important. This result you need to keep with you. Okay. Now, so after getting this result, we will go for the turbine work, like what is the work produced by turbine, because that is our main motive, because it comes under stage performance. In stage performance, degree of reaction, work, stage temperature fall, or pressure, stage temperature and stage pressure fall, that all everything will come under that performance, stage performance. Okay. Now, so we'll go for the work here. So turbine work, so basically this work is what produced, this work is what produced. So obviously it will come by the Euler turbine turbomachinery equations. Okay. And it comes under angular momentum equation basically. So direct I'm just going to write, because that derivation Euler's turbomachinery we had seen in compressor. So in the same way I will write direct result here. So the work or power produced by turbine. Okay. So how to get this? So first you write the specific work. Now we are having a specific work. A specific work produced. What is the specific work produced? So as per Euler's turbomachinery, as per Euler's for turbine. So it will be W is equal to U. Obviously that world component will come C2 CT2 plus CT3. This is the Euler's work, and obviously this will be the ideal work. Okay, this will be the ideal work, because Eulers will give the ideal work only. So now we have W is equal to U CT2. What is the CT2? It is CA tan alpha 2 plus CA tan alpha 3. Okay, tan alpha 3. Now we have UCA tan alpha 2 plus tan alpha 3, or we also have the result UCA. What is tan alpha 2 plus tan alpha 3? It is tan beta 2 plus tan beta 3. So ultimately the work produced by the turbine is nothing but U CT2, both you should know. In terms of velocity, this is in terms of velocity. In terms of angle, this is in terms of angle. Okay. This is very powerful result. you need to keep this value in box, and you need to remember this formula. Ultimately this is the result. Okay, you forget everything, no problem. You need to remember velocity triangle as well as this formula, because nowadays they are giving the velocity triangle. Some in few questions, if you check compressor or turbine, they had given triangle. So in triangle you need to like, that's the reason you need to learn velocity triangle. Like, they have given values, so you need to understand, okay, this is ct2 or ct3, or this is what c1 c2 or c3, or w1 w2 w3, what is alpha 2 beta 2, all those things. For that, two things are important. When you mug up this formula, that is okay, we have forgot the derivation, not required at all. This final result is required, but for this result also very much important is velocity triangle. You should know both things, then only you will able to solve the problems. All right, anyway, so this is what work produced, basically specific work. If you say what is the power produced by turbine, so obviously power generated by turbine. So what will be the power generation or power produced? It is, power will be the mass flow rate into specific work. Okay, so you can say it is m dot u ct2 plus ct3, or m dot u ca tan alpha 2 plus tan alpha 3, or it is m dot u ca tan beta 2 plus tan beta 3. This is what power generated or power produced, or power produced. Because it's a power generation device. All right, anyway, so this is the one thing, the milestone you have achieved here. Okay, now just like in the compressor you have seen the stage temperature rise, so state here also we will have, but will not have a rise, we will have a fall because we are having the sorry having the expansion in the turbine. Yes or no? So because of the expansion only, if you go for the enthalpy drop in a stage, you can write, so enthalpy drop or temperature drop in a stage, how to get that? So for this, you know, in this turbine we have a expansion, so we can say this is the turbine. Okay, in the turbine many problems we had solved in jet propulsion. So if this is the turbine, so definitely we will have a fall like this. This is the fall, this is the isentropic fall, and this is the actual. So for us in the turbine, if you check the stages, so stage is what, between 1 to 3, where it is here 1 to 3. So I can draw here 1 3, 1 and 3. So this is what 1, you can say this is what 3, this is 0 1, and this is the 0 3, this is the ideal. Okay, so if you check the work here, so whatever the work, this work is nothing but enthalpy H01 minus H03, or you can say Cp T01 minus T03, or Cp delta T we can write. Yes or no? So what is the stage temperature drop? You can get it. it is nothing but W divided by Cp, or you can say UCA divided by Cp tan alpha 2 plus tan alpha 3, or you can say U upon Ca divided by Cp tan beta 2 by tan beta 3. All right, so these are the temperature drop. Similarly, we can write, for this we can write the basically what is the pressure ratio and what is the pressure drop in stage, that also we can calculate. How we can do that? With the help of isentropic efficiency. Yes or no? So that isentropic efficiency, with the help of because the isentropic efficiency will be given to you also, okay, it will be given to you anyway. Now I hope this one is clear. Okay, so basically if you see the isentropic efficiency of turbine from this TS plot, this is what basically TS plot, this is T and this is isentropy. So if you draw, if you write the isentropic efficiency of turbine, isentropic efficiency of turbine, so it will be eta T, right? Eta T, just like for compressor eta C, here we have eta T. So it is nothing but actual drop of enthalpy divided by isentropic drop of enthalpy. So if you see what is the actual drop of enthalpy, so it is nothing but H01 minus H03 divided by H01 minus isentropic H03 dash. So this is the turbine efficiency, H01 minus H03 divided by H01 minus H03, or you can write in terms of temperature T01 minus T03 divided by T01 minus T03 dash. Check the diagram here. All right. Anyway, so this is the turbine formula. Okay. Turbine efficiency. You know that it is nicely explained in jet propulsion. Now, how to relate this with the pressure? So, if you have turbine efficiency, then you can write in terms of pressure ratio also. This value you can write. And very important, if you check here the value of temperature, check, this is nothing but, if you go for the enthalpy point of view, so here I must say in the stage, see, in the stage, because work is doing only rotor, so this is what nozzle, or this is what is stator. So for the stator, the enthalpy will be H01 is equal to H02. Total enthalpy must be constant, yes or no? And similarly, if you go for the in terms of the pressure also, so that total pressure will be constant across the nozzle, because it's not doing any work. No, it's not doing any work, and we are considering that the process is what, frictionless process. Okay. So if it is frictionless process, then P01 is equal to P02 across the stator. And same thing I had explained for the compressor also, but this rotor is the relative. So here the enthalpy will be H02 is equal to H03. But what is this? This is the relative only. Okay, this is the relative value. Always remember, dear, na? So because rotor is the rotatory part, no? Stator is the inlet guide vane, simply static part. So hence total enthalpy will be constant, and at the same time, if you say it is frictionless, so total pressure also be same. But in this case, your rotor, because it's a work producing component, no? Rotor is rotating and it is work producing component, so enthalpy will be constant, but total enthalpy, but it's relative because it is rotating part, rotatory part, no? It is rotating continuously. Anyway, that you also have seen in compressor. So anyway, now for this, if you go and calculate the in fact pressure, so you can do that. So eta t is nothing but you have now T naught 1 minus T naught 3 divided by T naught 1 minus T naught 3 dash. From here, if you check, you can write T naught 1 minus T naught 3 dash, and it is nothing but T naught 1 minus T naught 3 you had seen here, no? It is delta T, check. And delta T for what? Delta T for stage, no? So T naught 1 minus T naught 3 you can write, it is delta T for the stage, okay, divided by turbine efficiency. Now if you take common of T naught 1, so what you will get? 1 minus T naught 3 dash by T naught 1 is equal to delta T for the stage divided by turbine efficiency. T naught 1 in bracket 1 minus, this is what? T naught 3 by T naught 1 to whole power gamma minus 1 by gamma delta T of stage divided by eta T. Now if you check what value you will get, P naught 3, T naught 1, gamma minus 1 by gamma. This is for the turbine, okay. And this value, if I say, this is nothing but first I will write okay, let me write this one more step, delta T stage divided by eta T, turbine efficiency, and at the same time T naught 1 also will be multiplied. This will be the value, right? And if you take P naught 3 this side, then this quantity will be here 1 minus. So ultimately this is the value. If you want to calculate what is P naught 3 by P naught 1, this is what RE, expansion pressure ratio, no? And if you check this value, it is 1 minus delta T stage divided by T naught 1 into turbine efficiency to whole power gamma upon gamma minus 1, okay. What is the, this is the RE, expansion pressure ratio. In fact, this will be what? P naught 3 by P naught 1. This is the pressure ratio across the turbine, and from here you can calculate pressure drop also if you want, it's your choice, but here I am just going to stop this formula because it's your choice. If you want, you can extend this formula again. Pressure ratio I have calculated, you can calculate the drop also if you want, no? This is the formula. In compressor we had calculated RP, that was the compressor pressure ratio, and this is the expansion pressure ratio. Expansion pressure ratio across stage, that is RE. All right. Done.